Quick review of what I asked you to do for homework, and pretty much didn't get done, and we don't want that to happen anymore, okay? First week of class is confusion. We'll take more class time than we should to make sure everybody's on track with this, but in the future, make sure you review the videos and so forth. Take notes accordingly. I've talked a little bit about how to do that. The one thing you would probably want your notes from last time is this. There's more. And I think most of you have this theta versus t picture. Okay? And I said, don't be too compulsive about copying down what's on the board as in focusing on what's really important, what you're going to need to remember. It's a skill. It takes a long time to develop, years. So develop it as quickly as you can. It'll be to your benefit. Okay, so anyhow, if we have t and theta, here are your t's, here are your thetas. We were using counts of a pendulum, half counts actually, half series of a pendulum. But we just call them counts. You can call them something else if you want. Half swings. CT is easy to abbreviate. Okay, so anyhow, these are in counts. So we could say, okay, t is in counts, theta is in degrees. So when I calculate delta t, I'm going to have to subtract where we are from where we end up on each interval. So I'm subtracting 40 counts from 46 counts. I get 6 counts. Everybody did that correctly, so we understand that. Just make sure it's really here for reference. Then we subtract here, we get 8 counts. We subtract here, we get 18 counts. And I've got these in 360-degree increments if I did my arithmetic correctly. Check that. So we always have 360 degrees, so it's real easy to do the divisions. I chose these numbers so the divisions would be easy, so you don't have to spend time thinking about it. And of course, on the table I ask you to make, you don't have a lot of, most of your calculations are repetitive. Okay. So you got 60 degrees per count. And here you got 45 degrees per count. And of course, we're dividing the change in theta by the change in your count. Change in theta divided by change in count. That's what you always do for an average rate of change. And has it occurred to anybody what calculus concept this is leading to? This fundamental thing you learned first month of calculus? Okay. Okay, anyhow. Eventually I'm going to tell you, but keep thinking about it. What you learn in calculus. And here we're going to get 20 degrees per count. That's a little hard to read. But there we have it. Now I want to go on to calculating, or at least estimating the rate of change of omega. Okay? Does this look anything like this? It's of the same form, isn't it? Identical form. So, what is this? What's the name for what we're doing here?
Rate of change.
Calculating the rate of change, right? What are we doing here?
Calculating rate of change.
Calculating a rate of change. Make sense? Oh, very good. So now we want alpha bar. We're not going to be able to calculate alpha bar exactly, but we're going to be able to get a pretty good indication of the trend of alpha bar if we do this. It's going to be a little noisier and messier, especially in the early part of your data set, but it'll work. Okay, well, there's a complication here. We're going to need a delta T and a delta omega bar. Well, what's the first delta omega bar? Well, what column do you look at to find the change in omega bar? What column did we look at to find the change in theta? We looked at the theta column, right? For obvious reasons. What would we look at to find the change in t, the delta t? We looked at the t column, right? Just getting oriented to the table, okay? So what column are we going to look at to find delta omega bar? You've got to look at the omega bar column, right? Okay, so we got 60 degrees per count, 45, 20. Okay, so what's your first delta omega bar? Going to be minus 15 degrees per count, right? So this is and what's the next delta omega bar?
Negative 25 degrees.
It'll be negative 25. Okay, very good. Well, that was easy. Now we've got a complication here in finding delta t. Because this omega bar is associated with this interval, right? And this omega bar is associated with this interval. So we don't have just two numbers associated with this calculation for the delta t. We've got three delta t's involved. How are we going to get around that? Well, if you think about it, what we're looking at for any one of these calculations, we've got a couple of values of theta. Right? So these two values give us an omega bar. And then the next two values give us an omega bar. These are different omega bars. So I'm going to call this omega bar sub I minus 1. That's written a little small. And this one as omega bar sub I. And they're kind of run together there, so it's a little hard to read because it's small. But maybe I'll change that a little bit, separate these a little better. Okay? Now, maybe down here we have our some value of t, and another value of t, and another value of t, right? So maybe this is t sub I minus 2. Maybe this is t sub I minus 1, and this is t sub I. depending how we set up our indexes. Okay? Just to distinguish them, because I don't want to write omega for both of our omegas. Over on the table, then, well, okay, what's your best estimate of when this omega, well, let's just take omega I. Your omega I bar, your average omega I, depends on what two t's. Well, you got the first one, the second one, the third one. Which of those three?
Second and third.
Second and third, right? Okay, so second and third values of t were used to get this. Well, you use both the second and the third values of t. Which one are you going to choose to use to say that, well, I think this average velocity occurred at this time? At what time do you think this average velocity actually occurred? Well, it can get a little complicated, but the first order answer to that is fairly obvious. It ought to be about halfway between these times, right? Okay? So we're going to say that every omega occurs at the midpoint between the two times that we use to calculate omega. Okay? So I'm going to use a column here for T mid. So for this interval here, what's the midpoint time? 43, right? Halfway between 40 and 46 is 43. I'm going to use a formula. You add them together and divide by 2, but it's pretty obvious looking at these numbers that you can spot the midpoint. And it's fine if you got to do a calculation. A lot of times your numbers are such that you really do need to do a calculation. In 46 and 54, you've got 50. Yeah, 54 and 72, your midpoint time is 63 times. Okay? So now we can say that we think that this 60 degrees per count occurred at about 43 seconds. And 45 degrees per count probably occurred about halfway between the 46 and 54 at 50 seconds, okay? And then 20 degrees per count at about 63 seconds. So I'm going to change this delta t to delta t mid. So now for this calculation of delta omega bar, what two times would I use? Well, I would use the T mid for this, which is 43 seconds, 43 counts, and the T mid for this, which is 50 counts. Okay? So here, I'm going to say that the delta T mid is about 7 counts. And to be sure we're clear about how that was calculated, I'm going to say delta omega bar is approximately equal to I just wanted to write that delta T mid so bad that I wrote it too early. Sorry. Right here before your very eyes, I'm going to stop and think about what I'm writing. Okay? I'm actually capable of doing that. calculating delta T mid. Delta T mid is from 43 counts to 50 counts. Okay, those are the midpoints with intervals used to calculate the 60 degrees per count and the 45 degrees per count. Now this might be starting to get a little confusing. It's a good idea to remind yourself to take a look at the video. And we're at about 16 minutes and 30 seconds. Just to give you a clue there. Okay? So that's where this number comes from. And why? And then this number comes from here, and this would be 13 counts. Make sense? So we're trying to get a handle on how quickly this thing is slowing down. Okay? We established that it's slowing down, which is obvious in looking at it. What isn't obvious is how quickly it's slowing down. That's another level that we can't see easily with our eyes. Okay? It's not as immediately obvious as how fast things are moving. How fast is its speed changing? Actually velocity, and in this case it's angular velocity is changing, but we'll worry about those things a little later. So now alpha bar, well, it's delta omega over delta T, right? Okay, alpha bar is equal to delta omega over delta T. However, our data is not accurate enough to give us an absolute value of delta omega. We're just estimating the average velocity, right? And there's uncertainties in our data that make this kind of a noisy calculation. We'll see what happens later. Okay, so I'm going to say alpha bar is approximately equal to delta omega bar over delta T. So this is only an approximate alpha bar, because we don't really know omega bar that accurately. And we're using omega bar, not omega. Okay? So even if we knew omega bar accurately, we'd still just be getting an approximate value of alpha bar. Well, okay. Well, we'll go ahead and do this. Well, if you divide 7 by negative 15, you get, I think, negative 0.43. And that's in degrees per count squared.
Wouldn't you divide your negative 15 before your negative 15 over 7?
Yeah, the reciprocal of what I said. You gotta watch me. You really gotta keep an eye on me. Yeah, it's really easier to divide 15 by 7 than it is to divide 7 by 15. Okay, so it's negative 2 point, well, we've got a ridiculous number of significant figures. If you divide that out, you're going to get about 2.14. Okay? Well, that's ridiculous. I've got way too many significant figures. There's nothing in my data here that permits me to write that 0.14. Okay? I'm not even sure I'm going to be accurate in writing a negative 2. Okay? So I'm not really going to write 2.14. I mean, I could write what? 2.142. I can do it in my head. But I really don't want to embarrass myself. Okay, so now I divide negative 25 by 13, and what do I get? I get like negative 1.93 or something like that. Okay? And then I say, well, that's ridiculous. I might want to call that negative 2.1 and negative 1.9. But you know what it looks like? It looks like maybe I could suspect that this alpha bar thing is constant. Okay? So, we have a question here. First of all, come down here. Okay. I'm going to say, this is ridiculous. Our data isn't accurate enough to conclude that 1.4 and 9.3. This is better. Even though it's still not really justified. Okay? No, I'm writing too small for you to read. I'm just saying, really, negative 2 degrees per count squared, negative 2 degrees per count squared for the two quantities here might be appropriate. But just in case, we're going to at least do the negative 2.1 and the negative 1.9. They're a little more precise, but this is ridiculous. So really, we're going to use this. And we'll talk more, and you'll see more in your homework about accuracy of approximations and so forth. Okay. Now the big question. Suggested by this data. Is alpha bar constant? And that's a question you're going to attempt to answer by analyzing the data. Okay? Now, if you didn't write down enough data, email me and I'll dig out a video of one of these things and you can take your own data. You need a bunch of data. You need to know what your thetas are. So if you weren't writing it down every time, I think a couple people maybe didn't hear me when I said to do that. You're going to need to take 5 minutes and get some better data. Okay? It's only going to take you 5 minutes. I'll send you a link. Probably take me that long to find the darn thing. Okay? So, yeah, I don't mind doing that in the first week. Got to shake out the details. For launching a rocket, we probably have several holes. Okay. Yeah. Oh, I have something wrong here. We can't launch. Rocket's too expensive to waste. There are people on it and they don't want to die either. Okay? People can be picky about that. Okay. Now, what you're really doing here is analyzing some physics, and the physics primer is going to give you a lot of information. I might, if I can find time, I would like to do a video to support you a little bit with that physics primer. By the end, it's getting pretty hairy. And if you haven't had calculus, you're going to see, I think the last 4 problems involved calculus. Okay? So you're going to have to kind of, if you haven't had calculus, take it concurrently. You might have to put those 4 problems off for a few weeks. It won't take you long to get to the point where you can answer it, because it's really, well, some of the later problems involve integration, and we're not even going to get into that this semester, so that won't be a big deal. Yeah, the calculus you really need for this course is, first of all, understand what calculus concept this is related to. Okay? And I'm not going to tell you today. We need to ponder. It's a very, very obvious relationship, and probably somebody's taken calculus concurrently. We'll think of it, we'll see it quicker than people who've already had the calculus course, because our calculus courses, the way students approach them, maybe the way we teach them. People really don't understand what the heck they're doing. Okay. You learn some rules. You learn to do some manipulations. Well, manipulations are important because you can't do calculus without doing the manipulations. If you don't know what the manipulations mean about the real world, well, we probably need to include more of that stuff. Okay? That's going to be obvious when I tell you, if I have to tell you. See a bunch of people. I didn't think of that. Okay? Really obvious. Now, what's going on with this thing? Okay, it's slowing down. What we're getting to with this alpha bar is how quickly is it slowing down. That's important. Okay? If you're in a car, and for one reason or another, you got to slow down fast. Maybe an elephant's walked out in the road or something. That happens, doesn't it? Okay? How many people had to stop for an elephant? Practically everybody, right? Yeah, I mean, eventually, though, it scared all the elephants away, and we don't have to do that as often. Okay, well, you know, you have cases where you need to slow down. Something goes out on the road, you don't want to hit a deer, it's going to wreck your car. Maybe cause you have a problem, too. I came really close. It was on a curve on the West Virginia Turnpike. You're going about as fast as you go around that curve. All of a sudden, a deer ran out in front of me. Wouldn't have been good to hit that deer. So I swerved about as much as I could swerve, about as fast as I could swerve, and I swear I couldn't have missed that deer by a foot. Oh, that was about 8 inches. Okay? Yeah, thing come out of nowhere. I would have had a serious chance of being killed if I hit that deer. Probably wouldn't do good for the deer either. You know, you drive long enough, you're going to have a lot of close calls. So you better know how to slow down fast enough. Better know how to swerve and not swerve too quickly. Sometimes, of course, there's no choice. I mean, either way, you'll have an accident. That happened. Okay, well, depressing news, because I sure know none of you suspected any of this. But depressing news aside, how do you determine how quickly you're slowing down? What can you do to determine how quickly you're slowing down? Everything in your instrument panel might be helpful. You got your speedometer, right? I actually got your odometer, but that's not going to be very helpful because used to be odometers moved continuously. They weren't electronic. So you kind of estimate where you were with some accuracy down to 1/100th of a mile. Okay, they showed tenths of a mile, and they kept rotating. And once this thing went around once, this thing went 1 unit. Once this thing went around 10 times, this thing went 1 unit. So this one measured tenths of a mile, this measured miles, this measured tens of miles, and you get your decimal output. So if you happen to see one of those, don't be frightened. Standard technology. It's been around for well over 100 years. 100 years ago, I had one on my bicycle. Quite a few years ago. Okay. Theoretically, you could use that. If you're not slowing down too quickly, you could actually be fairly accurate because that would be totally analogous. If you have some way of doing your time and figuring out how many miles your vehicle had traveled, you could find the rate at which the distance changes with respect to time, right? Well, that's how fast you're moving.